refers to how much salt is required at the interface of steel to make the steel to corrode. Okay. 3 is coming at a given time. So it could be 3 per second, it could be 5 per second here. A lot of seconds will have to evolve to change for the threshold here to reach a certain value. Okay. We don't have an agreed threshold yet. We can't simply agree it. But what we know, most standards would say 0.5% by weight of binder can be taken as the chloride threshold. Okay. We have seen concrete corroding with 0.2. We've also seen concrete not corroding for nearly 1. Depends. It depends on other factors. Clearly depends on the pH as well. So threshold refers to the chloride at the interface. So it's the accumulated chlorides that's coming in. Binding refers to flow and the reaction part of the flow. Okay. They are distinctly different. So any replacement material with high volume of aluminates or calcium silicates, extra calcium silicates, so GGBS, PFA, Metacal, any of them, they will have a higher binding capacity than Portland cement. Okay, because of the fact that they have aluminates and other things. Portland cement might have a higher threshold. So the threshold might be higher for Portland cement. I have a reason for saying might be, because threshold is very much connected by the work Rashid Usafir and a few others did years ago. They connected chloride threshold to the hydroxide concentration. And they were saying that chloride should be referred to as chloride divided by hydroxide concentration, basically pH. And they had good reasons to say that. It's a very consistent result. Which means Portland cement has higher pH. So Portland cement highly likely will have a higher threshold. Okay. But replacement materials will have extremely low flow rate. So you'll have to balance this. If I had a choice, I would spray the steel with Portland cement and then I'll pour GGBS 79% concrete for chloride environments if I had a choice. But that's not feasible, that's not realistic. So, does that answer the question? Any other questions on chlorides? Chlorides are a big topic, okay? This is where you're going to make your money if you're into concrete testing or consultancy. This is where you can make your money. So, where did we go? So our challenge was to go from a laboratory-based test where you need a core sitting in the middle of it, to the surface. I mean, we were always looking at surface-based tests. We didn't want to take a core. There are different reasons for that in the UK, okay? First of all, taking cores is not feasible for certain kind of structures. Okay. Taking cores require you to send somebody to take the core and bring it back. It is costly in the UK, it's costly in Europe. And thirdly, depending on access, it may not be that easy to take cores. Core is quite a heavy machine. You're going to have anchor points to core it to. Okay. So we were looking at tests that can be applied on the surface and does the job. So we then came up with this test, which is a prototype is what you're seeing there. Somebody was asking me yesterday, how do we develop these tests? We take a material called Perspex, which is a clear glass kind of plastic, and we core it and we make the cells that we need. It's a very easy machine. Nowadays you can buy a 3D printer for £30,000, it'll do the same job. So we machine it and we make everything ourselves. We have a technician support for that. I could take that and then put that together in no time. But that's not the prototype that's available now. Once the companies take over, then it looks much more tidier, neater. During my PhD, I haven't seen this. I've only seen it in an extremely messy format. So the test works very simple. You have the surface here that you can see, and you have a water chamber where water is stored, and inside here is a chamber where salt is stored. So it's a coaxial system. You have salt in the middle and you have water surrounding it. And there is a negative electrode here and there's a positive electrode here. The negative electrode comes all the way down and sits at the bottom. So essentially what it does is it'll create a flow of chlorides. It'll force chlorides from the middle to go into the concrete. That's the only place it can go. And once it goes in, this red electrode that you're seeing here will pull them back. So it will go in and it will come out in a J sort of shape. It's very simple logic. So essentially what you get is if this is your concrete surface and that's the inner part of the cell and this is the outer part of the cell, there's one of your electrodes which is negative, there's your other electrode which is positive. So the flow happens like this. Okay. At the start of the test, we were worried that this is going to be a non-steady flow because there's chlorides going to go all the way down and then come back. But the chlorides that are going to do a shortcut, they're still going to do the shortcut. So we were worried that this is going to be a non-steady test. It's not that we were worried, but mathematically that's challenging. Steady test is a bit more easier mathematically. But as it turned out, we get a very similar path as this. That's because this area dominates the flow. Okay? So in this test, what you're getting is very similar to that result, but it is a pseudo result in the sense some of the chlorides will go out and out. But because I'm only looking at what's coming here, I will get a very similar curve. But the value that I get, the slope that I get will be much smaller than if I use that kind of test. Okay? That is to do with the fact that I may have 100 chlorides going out, but it's only 80 of them coming back steady, so I'm losing 20 of them in the flow. Okay? But that's okay because I'm looking at the steady state part of it. So that's permit. Any questions? So it's a steady state test. It cannot tell you anything about non-steady part of it. That's what we're working at the moment because it's a continuous monitoring system. It measures the chloride concentration coming in this cell. There's a conductivity sensor sitting in it. It keeps on measuring the conductivity and converts it into chlorides. Along with that, it measures the current. So the current can be used to get your 6 hours RCPT value if you want. I would not recommend it, but you can have it. And the current will also be monitored throughout. So we know roughly looking at the current when you're going to reach this state. Okay. The third thing is it measures the temperature in the cell. So altogether, it's quite an advanced piece of instrument for its nature. But it's not without limitations, okay? All of these tests have limitations. Can you tell me the first limitation of that test? What is it pushing into concrete? It's pushing chlorides into concrete. The very thing that you're trying to avoid. But the amount of chlorides that is pushing in is so small that it's nominal, that doesn't really affect your steel that much. But it still does push chlorides in. So if you're going to do that for testing any pre-stressed tendon-based concrete structures, I would be very cautious. You should be testing areas where you don't have any of those major structural parts. You can ask whether we did work on different other ions. We did, but all of them fail to give you very close results. We know we can use nitrates, it'll do the same sort of behavior, but it takes hours, it takes days to get a result. A test can finish within 24 hours, 6 hours most of the time, 24 if you're using extremely good quality concrete. If you're using super high performance concrete, the flow will be limited to the surface, very much surface. You're talking about 5 millimeter if you're lucky. That's because that concrete is extremely dense. You shouldn't have to test them. Okay? Anybody using the test, I would suggest them to take a cube or take a slab, test it, break the slab, look at the chloride concentration in the slab by spraying silver nitrate. It gives you a feel of how far does the chlorides go, what other results do you get. Okay. So any test that you develop, and hereafter the slides are to tell you if you are to develop your own test, what are the things you should do. First of all, it's a new test, so the results from the new test should be on the x-axis, okay, and the results from standardized tests should be on the y-axis, and you have to check whether they correlate. Not necessarily it will correlate all the time, but that's okay, because depending on where you're taking the observation from. Because it's a steady state test, we know the correlation with steady state tests will be the highest. Okay, it's concrete we're testing, so experimental variability aside, we got 93% correlation between what you get from permit and what you get from a split cell test like that. Okay. Note that it's not equal. If they were giving the same measure, they should have been equal, right? They're not. This value is lower. It's about 78% lower than what you get here. That's to do with the fact that you're losing chlorides. Okay. Now, moving over, we looked at the comparison between non-steady state test and the permit that we've developed, and we can still see there's a stronger correlation. Okay. That can only happen to two factors. One is that permit is measuring in this region, which it's not. It's definitely not measuring in this region, but it might be measuring the flow coming back at different times. So it could be a pseudo region somewhere here. Second, what's commercially available as a non-steady test may necessarily not be a non-steady test. Okay. We've left it at that because I didn't want to challenge this one. But it does correlate reasonably well. And I know the correlation will drop. That will drop if you're using high volume replacement. If you're using concrete with extremely high binding capacity, it'll drop. That is to be expected because extreme binding capacity means this period will be dominant. Okay. You should also note that the correlation is significantly favoring the non-steady state test because the coefficient there will be much higher than steady state. It's to be expected. Okay. So that's how you should, if you're going to develop a test of yourself, this is what you need to do to prove that our test is better than others or our test is as comparable as others. Okay. So coming back to the durability things, so we looked at transport and we looked at autoclam and a lab-based sorptivity test. We looked at the chloride diffusion or migration test, and we looked at a site-based chloride diffusion migration test. The other thing we need to look at is the strength of concrete. Okay? How do you assess strength of concrete? At the moment, if you were to assess strength of concrete for a structure, how do you do it? Just go with the coring machine and just core into the concrete. Is that what we do? Morning. Oh, thank you very much. how do you assess strength of concrete? An existing structure, you've been asked to assess the strength of an existing structure. What's your first protocol? A reborn hammer? Did anybody say reborn hammer? Okay. What else? Okay. Pull off. What was it? Sorry. Core. Basically taking a core and you bring it to the lab to do the testing. Okay. Is core a cylinder or a cube? Okay. So what you're getting is a cylindrical core strength, and the diameter of it will have a relationship in what values you get. So you know all of that stuff. Good. You can't core the entire structure clearly. Okay. So you'll have to limit the cores. So you said UPV, reborn hammer, core. Did I miss anything else? Pull out. Okay. Which one is the reference? Do you relate everything back to a reference to say this is the actual core? So your core is your reference. Yeah, perfect. And then everything else is a benchmark to that. Okay. So good practice will be to identify a location, do all your tests, and core from one of those locations so that you can relate everything back. So you can benchmark your UPV, you can benchmark your reborn hammer and your pull-off test and everything. Make sense? Okay. And you will also do that in maybe multiple locations, not just one location. Okay. Can you relate the UPV result from structure A to the UPV results from structure B? Let's say you got 4,200 meter per second. Is that how it works? Yeah. As the velocity in one structure. You got 4,200 in another structure. Does that mean they have similar strength? What factors does affect it? Asking questions gives me time to drink my coffee. Ultimately, the concrete could be different, the aggregate could be different, the cover depth could be different. So all of these will have a factor, and those who are doing the work will also know the technician can actually influence the test as well. Not purposefully, they might have an inclination to do the test in a certain way. I think the angle also matters, I think. So in our case, we suggested, we use all of these, okay? I like all of these tests as an integrity test, because this is such fast test is the only thing that you can do to get a spread of results across a larger section. As engineers, our decision is on the whole structure, not on the core, not on the tiny part of it. It's on the whole thing. So you need something that will allow you to spread out. And this gives you the perfect reason for it. In the 1980s, measuring strength was a priority for UK. So in response to that, the guys decided to develop something called limpet. Okay. Now, looking 30 years later, I can say that this test has been very successful, and a lot more tests have developed around it. Now that this is almost a standardized procedure, not the test but the pull-off mechanism. They've realized then that if you're to glue a disc onto the surface and you pull the disc, the force that's required to pull is related to its compressive strength or tensile strength. Okay? And that's what the direction they were trying to follow. And later on, now we know that there's different versions of it. There's a lock test. You can put the stuff in and then better figure. Maybe I'm standing too far. They had another reason for doing this. The reason was debonding between tiles. Okay, so you have a perfect concrete surface, and then you put a tile or another surface on the top of it. They wanted to know the bond strength between the two. And that's where the test came in handy. What they did is they drilled a core just so that you reach the parent layer or the bottom layer. Then they attached the disc on the on the surface. Visualize it. Yeah. So it's your original surface here. You put your tile or something else on the top. You wanted to know the bonding between the tile and the parent concrete. So you drilled using a core all the way down to the surface of the parent material. You put the disc on the top of the tile and you put the disc. So when you pull it off, you're either going to break the glue between the disc and the tile, or you're going to break the bond between the tile and the concrete. And that's what you're looking to assess. Quite often you might break the glue. That's a bad failure, so you do that again. If you look at the epoxy glues available now, they are super strong, so you can do n number of tests. In the 80s, they really had to make their own glues to get that working. But that's what the test was used for, and that's what the test still is very useful. Imagine these tiles being vertical, or these marble facades being vertical. You really don't want them to fall. They're extremely dangerous if it falls. So the test would be performed either in a laboratory situation or on site. But it does have the issue that it'll